Greetings, AP Chemistry students. Today I'm going to show you how to work through the problems on this gas equilibrium problem set. So for problem number 1, they give us moles of each of these things in a 2-liter vessel, and it asks us what Kc equals. Well, K equals the concentration of hydrogen squared times S2 over H2S squared, because everything's a gas. So we start plugging things in, except we put in molarities, and molarities are moles over liters. So for the hydrogen, if we have 0.2 moles in 2 liters, that is 0.1 molarity squared. The sulfur gas concentration, 0.8 in 2 liters, is 0.4 molar divided by, and for the H2S, it's 1 mole in a 2-liter vessel, so that's 0.5 molarity squared. So then into our trusty calculator, we do 0.1 squared times 0.4 divided by 0.5 squared, and we get 0.016 molar, which is answer choice D. In number 2, if equal moles of A and B are added to an empty flask, then when you reach equilibrium, well, your equilibrium position will shift to the right because you don't have any of the products to begin with. So the reaction will proceed to the right. So as you shift to the right, you're going to make 3 times as much C as you do D, and you're going to use up twice as much A as you do B. So at equilibrium, your A will be less than B, and your C will be greater than D. So the answer choice that fits that is option D. We don't know to what extent this reaction goes because we don't know the value of the equilibrium constant to evaluate whether it's a large or small constant. But equilibrium will occur further to the right than having all reactants. So that must be true. Number 3. In this problem, if it asks us the value of Kp, well, Kp equals products. Well, our product is a solid. We don't include the pressure of a solid, divided by the partial pressure of NH3 times the partial pressure of H2S. And that doesn't seem to match any of these, so the answer to that is E. For number 4, it's giving us a equilibrium constant and a equilibrium reaction. An equilibrium mixture contained 0.9 moles of carbon monoxide, 0.25 moles of water vapor, and 0.5 moles of hydrogen gas in a 5-liter container. How many moles of carbon dioxide were there? Well, first of all, you put concentrations, not moles, into your equilibrium expression. And our equilibrium expression says that K equals concentration of CO2 times H2 over CO times H2O. And so that's equal to 5, because it tells us that. So 5.0 equals. Now, we need to convert these into molarities. We don't know the molarity of CO2. The molarity of hydrogen gas is going to be 0.5 over 5, or 0.1, because it's in a 5-liter container. The molarity of carbon monoxide is 0.18, and the molarity of water vapor is 0.05. So the concentration of CO2 equals 5 times 0.18 times 0.05 over 0.1, 0.45 molar, and that equals moles over 5 liters. So that's 2.25 moles. So the answer is A. Number 5, it says, under the same conditions as in question number 4, 0.4 moles of H2 and 0.4 moles of carbon dioxide are placed in a 1 liter vessel. What will be the equilibrium concentration of water vapor? So for this, we're starting with 0.4 moles of this in a 1 liter, so that's 0.4 molarity and 0.4 molarity. This has to go down by some value x, and these go up by some value x. So at equilibrium, we equal x, 0.4 minus x, and 0.4 minus x. So if we plug into our equilibrium expression, 5 equals 0.4 minus x times 0.4 minus x over x times x. We could simplify this to say that 5 equals 0.4 minus x squared over x squared. And then we can just take the square root of everything. So the square root of 5 is 2.24 equals 0.4 minus x over x. So 2.44x equals 0.4 minus x. So 3.44x equals 0.4. X equals 0.4 over 3.44, 0.116 or 0.12 molarity, and that is the concentration of the water and the carbon monoxide. So that's our answer. For this one, we could not use our approximation that x is very small because our equilibrium constant is not very small. But we can just use the fact that everything is squared, and we can just take the square root and do it. But just remember, you will never have to use the quadratic equation. This is just an interesting case where we have to use another little math trick that we know. For number 6, which of these has the least tendency to go to completion? That's going to be the one with the smallest equilibrium constant. So that would be B. Negative 31 equilibrium constant has the least tendency to go to completion. Problem number 7, we are going to omit. And let's look at problem number 8. It says at 30 degrees, an equilibrium mixture of dinitrogen tetroxide and nitrogen dioxide exerted a total pressure of 0.74 atmospheres. The partial pressure of N2O4 was 0.5. What's Kp? Well, Kp equals the pressure of NO2 squared over the pressure of N2O4. Now, they tell us the pressure of N2O4 is 0.5 atmospheres. And if the total pressure is 0.75, then the partial pressure of NO2 must be 0.75 minus 0.5, which is 0.25 atmospheres. So we take 0.25 squared over 0.5, and we get 0.125 is the value of K. So that's C. And last, but certainly not least, problem number 9. We have this equilibrium mixture, and then it wants to know what would happen if we add all this extra stuff. Well, first, let's calculate what the value of K is. So K equals concentration of HI squared over H2 times I2, which is 0.7 squared over 0.1 times 0.1. 0.7 squared over 0.1 is 49. So now this is saying if we suddenly add all this other stuff, what would happen? So if we add that, then our H2 concentration would be 0.15. Our I2 concentration would be 0.15. And our HI concentration would be 1.05. So let's see, are we still at equilibrium? Well, if we plug those numbers into our equilibrium expression, 1.05 squared over 0.15 times 0.15 equals 49. So this expression is still equal to our equilibrium constant. So that means that nothing is going to happen. E, no net chemical reaction would occur. So I hope that helps, and y'all have a great day.